artificial intelligence. It's not just a buzzword anymore, is it? It's reshaping everything around us. I mean, how we work, how we learn, even the apps we tap on every single day. We're talking about systems that can write code, create art, even, help diagnose diseases, pretty wild stuff. But have you ever stopped to think, what actually powers all this? What's really going on under the hood to make these incredible systems work? What if I told you the real power isn't just algorithms, but more like a bare-knuckle brawl happening right at the foundation of tech? We're talking about the AI chip. And the stakes, they couldn't be higher. So today, we're diving deep into that whole arena. We're going to explore how the biggest names, Google, Amazon, Microsoft, are really challenging NVIDIA's long, almost unshakable dominance in AI accelerators. Our mission is to unpack the strategies, the engineering, the shifting power dynamics that are basically redefining the future of AI. We'll look at why this shift is happening, the different ways these giants are tackling it, and what it all means for how AI gets built and used. So let's get into it. Okay, so for, over a decade, NVIDIA has just built this undisputed empire in AI hardware. Their name, their tech, it felt like it was AI development, didn't it? The absolute go-to.
It really was. But it's not just about the silicon, the hardware itself. The real genius, and honestly the biggest wall for competitors, is their software moat. CUDA. CUDA isn't just code. It's like this whole universe developers operate in. It stands for Compute Unified Device Architecture. Launched way back, 2006 actually. Think of it as this massive layered platform. You've got programming models, compilers, libraries like Cuddn for deep learning, Kubernetes, NCCL for multi-GPU stuff. It basically made parallel processing on GPUs accessible for, millions of developers. And that created huge developer inertia.
Inertia, meaning it's just easier to stick with what you know.
Exactly. And incredibly high switching costs. It locked in a whole generation of AI talent into NVIDIA. Yeah. Trying to move meant learning a whole new way of doing things, rebuilding tools. It was, and still is, a massive hurdle.
And that kind of lock-in, that position, it led straight to what everyone started calling the NVIDIA tax. Now, just to be clear, this isn't like an official government tax or anything.
Yeah.
It's just a term people use for NVIDIA's, frankly, extraordinary gross margins on their data center GPUs. We're hearing numbers like 80, even 90%. So like an H100 GPU might cost NVIDIA maybe $3,000 to $5,000 to make, but they sell it for $20,000, $40,000. That's a massive premium.
Yeah, it's pretty staggering. But that kind of pricing, while great for NVIDIA, creates huge problems for their biggest customers, the hyperscale cloud providers. Two main things. First, the sheer economic burden. AI compute costs are insane. For OpenAI, estimates were like 55–60% of their total operating expenses in 2024, just for compute.
Wow. That's unsustainable.
Pretty much. And second, it's a strategic vulnerability, being totally reliant on one supplier. That leads to bottlenecks. Lead times for top NVIDIA chips stretched for months. Plus, these cloud giants had almost no control over their hardware roadmap. They're kind of stuck in NVIDIA's timeline of decisions.
So, okay, it sounds like for Google, Amazon, Microsoft, building their own chips wasn't just a nice-to-have. It became absolutely necessary, an imperative.
Oh, absolutely an imperative. You can't have your most critical resource, the engine of your future growth, controlled by a single supplier charging that kind of premium. It just didn't make sense long-term. So this in-house imperative really kicked in, driven by, I'd say, three main things. One, cost. Plain and simple. Bypassing the NVIDIA tax. Google's TPU program, for instance, reportedly gets them AI compute at maybe 20% of the cost of buying NVIDIA GPUs.
20%? That's a 4 to 6 times cost advantage.
Exactly. At their scale, that's billions saved, which ties into the broader idea of total cost of ownership, TCO. It's not just the purchase price.
Right. It's the long-term running cost, too. Power, cooling.
Precisely. Yeah. Which brings us to point two, workload-specific optimization. NVIDIA GPUs are general purpose. They do lots of things well. But application-specific integrated circuits, ASICs, these custom chips, they are designed from the ground up just for neural networks.
Like a race car versus an SUV.
Perfect analogy. They deliver much better performance per watt, which is huge in data centers. Lower power builds, better efficiency.
Makes sense. And the third reason?
Control. Supply chain control and strategic differentiation. Building your own silicon gives you technological sovereignty. Think Apple and their M-series chips. They design the core. It lets them integrate everything deeply, create a unique advantage, control their destiny from the silicon right up to the data center concrete.
Okay, so the stage is set. NVIDIA's dominance, the rising costs, the strategic need. So who stepped up first? Let's talk Google. Their tensor processing unit, the TPU, feels like the most mature effort out there, a decade-long bet.
It really is, and the evolution is impressive. TPU v1 back in 2015. That was inference only, used internally for things like you
Yep.
mentioned AlphaGo. But TPU v2 in 2017, that was the game changer. A huge leap. It added training capabilities, introduced bfloat 16 format, and
Mhm.
crucially, TPU pods.
Pods, like linking chips together.
It's exactly 256 chips networked as one giant supercomputer. And importantly, they made it available on Google Cloud for others to use. Then TPU v3, double performance, added liquid cooling, scaled to over 1,000 chips. TPU v4 in 2020 brought optical circuit switches OCS for super flexible networking, scaling to over 4,000 chips. And just recently, TPU v5 split into v5e for cost-effective inference and v5p for raw performance, really taking aim at Nvidia's H100.
And there's more coming.
Yep, TPU v7, codenamed Ironwood, expected 2025. Focus on inference efficiency, aiming for double the performance per watt of their current gen, plus a massive jump in memory per chip.
So Google's clearly innovating not just on the chip itself, the matrix multiply unit or MXU, but the whole system, the TPU pod architecture, their own interconnects, the liquid cooling. It's a full stack approach.
Absolutely, but hardware is only half the equation, right? You need software.
Google's answer to CDA is JAX. JAX is powerful. It combines a NumPy-like feel with their XLA compiler for speed, automatic differentiation, easy parallelization. It's great for researchers pushing
He
boundaries.
sense a but coming. Huh? Yeah, there's a but. JX has a really steep learning curve. It uses a functional programming style, which is quite different from PyTorch, the most popular
Hey,
framework.
if you're a PyTorch developer,
It forces a big shift in how you think and code. Plus, it's still officially experimental, and debugging can be tricky, let's just say opaque. It makes PyTorch support feel a bit like a second-class citizen compared to native JAX.
okay, that's a key trade-off. Huge power, but a tough learning curve. So summarizing Google, deep integration, big TCO advantage, sophisticated chip strategy, but maybe a bit of a software adoption challenge with JX. Still a decade-long bet paying off. All right, let's pivot to Amazon. AWS, they took a different path, didn't they? A two-pronged attack. Trainium for training, Inferentia for inference. Why split them?
Well, Amazon's core bet is that training and inference are just fundamentally different beasts computationally. Training is this brutal offline task, needs raw math power, tons of memory for things like backpropagation. You're teaching the model. Inference is live, real time. Priority is low latency, high throughput, power efficiency. You're using the model.
So trying to do both perfectly with one chip involves compromises.
That's the bet. By specializing Trainium for the heavy lifting of training, Inferentia for fast, efficient inference, they aim for optimal performance in each domain, like having specialized tools instead of one multi-tool.
And the chips reflect that. Trainium 2, big boost, lots of compute, tons of memory, neuron link for connecting them. Inferentia 2 focused on throughput, low latency, better power efficiency for running models live.
And their software bridge is the Neuron SDK. Their approach here is more pragmatic than Google's JAX. They aim for native integration with PyTorch and JAX, trying to minimize code changes for developers. They've also got good ties with Hugging Face through something called Optimum Neuron,
Sounds developer friendly.
in theory,
Right.
but we still hear from developers that there's friction. Sometimes getting models optimized takes significant effort compared to, say, just running on CUD. It's not always seamless.
But Amazon has that huge partnership with Anthropic, right? The Claude AI folks. Billions invested and Anthropic committed to using Trainium and Inferentia. That's got to be huge validation.
Oh, massive. It's a huge strategic win. It validates their hardware and creates this virtuous cycle. Anthropic uses it. Others see it works. Maybe they try it too. It feeds into Amazon's whole extreme vertical integration strategy.
Still, you mentioned some sobering numbers earlier.
Yeah, the reality check. Those leaked internal AWS docs from April 2024, Trainium at only 0.5% of NVIDIA usage, Inferentia at 2.7% among top customers. It just underscores how hard it is to displace CUDA, even with specialized hardware and big partnerships. The ecosystem gravity is immense.
Okay, rounding out the big three. Microsoft. Their approach with the Maya accelerator sounds ambitious. Co-designing the whole stack, silicon to cooling?
It really is holistic. Microsoft's thinking goes beyond the chip. They're designing custom server boards, custom racks, optimized for AI's power and networking needs. And their cooling solution is pretty innovative, this Sidekick liquid cooling unit that works within existing data center layouts. It's very system-level thinking.
And the chip itself, Maya 100. Specs sound solid. TSMC 5M in ear, over 100 billion transistors. HBM memory, their own MX data format.
On paper, yes. But this is where the challenges seem to surface. Reports suggest Maya 100, designed before the current LLM boom, might have some architectural issues for today's huge memory-hungry models. As of late 2024, word was it was still mainly in internal testing, not powering major services like ChatGPT or Copilot yet.
And delays for the next versions.
Yeah, successor chips like Braga reportedly pushed to 2026, and Klee aiming for Nvidia parity even later. It just shows how incredibly hard this semiconductor game is. Timing is everything.
But their software strategy seems different again, betting on PyTorch compatibility, using OnNX runtime, leveraging Triton from OpenAI. Sounds like they're trying to make it easy for developers.
Exactly. It's a pragmatic, developer-friendly path. Minimize the friction, leverage the existing open source world. It might mean not squeezing out every last drop of peak performance, but it lowers the barrier to entry significantly.
So putting it all together for Microsoft, it sounds like maybe the least mature of the three custom silicon efforts right now, facing some real execution hurdles.
That seems fair based on reports. The delays could definitely strain that critical OpenAI partnership, potentially keeping Microsoft as a major Nvidia customer longer than they'd like. It's a tough spot.
Okay, let's talk about a moment that really shook things up recently. OpenAI deciding to use Google Cloud's TPUs. That broke their exclusive reliance on Microsoft Azure. Huge news.
Absolutely seismic.
Mhm.
And the reasons are multi-layered. First, just sheer need. OpenAI's compute hunger is astronomical. No single cloud could likely satisfy it fully. Second, strategy. Diversification reduces risk. If there are shortages of one chip type, they have another source. It also gives them more leverage with Microsoft.
And cost. Was that a factor?
Almost certainly, especially for inference. Using Google TPUs is a pretty strong signal that, for certain workloads, maybe inference, Google's TCO, total cost of ownership, is very compelling. Though it's interesting, reports suggest Google isn't giving OpenAI their absolute top-of-the-line newest TPUs. Bit of competitive balancing there.
So what are the ripple effects for OpenAI, for Google, for Microsoft?
For OpenAI, it's a declaration of independence, really, a vital second source of compute. And it rebalances the power dynamic with Microsoft. For Google, a massive strategic win. Huge validation for the TPU program, boosts Google Cloud's AI cred instantly. But yeah, the paradox is fascinating. They're helping fuel a company that's a major competitor to their core search business.
Selling shovels during a gold rush, even to your rival miner.
Pretty much. And for Microsoft, it's undeniably a blow, strategically and narratively. Loses that exclusivity, raises questions about Azure capacity or cost effectiveness for OpenAI's needs, weakens their leverage.
So this OpenAI-Google deal feels like a real watershed moment.
Totally. It proves that a high-performance, scalable, non-Nvidia ecosystem is real and practical now. It shows that cost and strategy can push even the biggest AI labs to switch, or at least diversify. That's going to encourage a lot more companies to look beyond Nvidia. The game has definitely changed.
Right, so it's not just about raw chip speed anymore. We need to compare across performance, yes, but also developer experience and that crucial total cost of ownership, TCO.
Exactly. If we look at benchmarks like MLPerf for performance, NVIDIA's Hopper and now Blackwell chips still generally lead in raw training speed at scale. Like that GPT-3 training run, 3,000 H100s beat 4,000 PPU V5s time-wise. And Blackwell looks like another big jump.
But inference is different.
It's more nuanced, yeah.
Yeah.
Google's TPU V5e showed great performance per dollar gains. NVIDIA's L4 inference chip also showed strong perf per dollar. But what's telling is the lack of public MLPerf numbers for Maya, Trainium, Inferentia. It makes direct comparisons harder.
Okay, then developer experience. We touched on this, but it's critical. CDA is the default, right?
Yeah, it's the incumbent. Mature, huge ecosystem, 15 plus years. It's the path of least resistance. Like driving on a familiar highway. Google GAX. Powerful, research-focused, but steep learning curve, functional programming, tricky debugging, maybe a high-performance racetrack, but you need special training. AWS Neuron, pragmatic, tries to work with PyTorch JAX, aims for minimal changes, but developers report friction. Maybe a newer highway, still some construction zones. Microsoft's PyTorch Triton path seems the most open, developer-friendly, minimizing friction, maybe sacrificing a tiny bit of peak speed for ease of use. The accessible main road.
And all this leads back to TCO, the bottom line for these cloud giants.
Absolutely. TCO is everything. You have hardware costs, the Nvidia tax versus cheaper custom ASICs. You have power and cooling ASICs often win on performance per watt, saving millions on electricity. You have system and networking costs, which hyperscalers optimize when they design everything. And then the hidden cost, engineering effort. CDA minimizes this. JX or Neuron can add significant overhead. So structurally, custom ASICs offer a TCO advantage. They compete not just on speed, but on intelligence per dollar or performance per TCO. But NVIDIA isn't just sitting back watching this happen, are they? They must have a counter strategy. Oh, absolutely not. NVIDIA is playing offense. It's a multi-pronged defense of their kingdom. First, relentless innovation. The Blackwell platform, B100, B200, the GB200 superchip, it's a beast. Multi-die chiplets, 208 billion transistors, new transformer engines, faster memory and networking, a huge performance leap over Hopper. Second, they're moving up the stack. They're not just selling chips anymore. Nvidia AI Enterprise is a software suite. DGX Cloud lets you rent Nvidia's own AI infrastructure. They're becoming a platform and cloud provider competing directly with their customers.
Wow. Competing with Google Cloud, AWS, Azure, bold.
Very. Third, a really clever move.
And
Feeling Fusion. This lets other companies plug their own custom chips into NVIDIA's platforms.
wait, embracing the competition?
Sort of. It keeps NVIDIA's NVLink networking at the center, lets them sell high-margin interconnects, and maintains their platform role even if others bring their own compute. Very shrewd. And fourth, expanding their customer base. They're aggressively going after sovereign AI deals, helping nations build their own AI clouds, and targeting the broader enterprise market, partnering with server makers, boosting smaller GPU cloud providers like CoreWeave, diversifying beyond the big hyperscalers.
Okay, bringing this all together. The AI hardware world is clearly shifting. It's not just NVIDIA's game anymore. We're moving towards a more complex, fragmented future. General purpose GPUs alongside specialized custom chips.
Definitely. And there are key trends to watch now. One, the battle for the software layer. Can someone create a truly hardware-agnostic way to program AI, like OpenXLA or Triton, that works everywhere? That's a huge prize. Two, interconnects. The network between the chips is becoming as critical as the chips themselves for scaling big models. That's the new bottleneck. Three, inference rules. Training gets the hype, but running models day to day. That's where most compute cycles will be. Demand for cheap, fast, efficient inference chips will explode. And four, TCO is king. It's not just about raw speed anymore. It's about the cost per answer, the intelligence per dollar, optimizing the whole stack.
So, this whole evolving landscape, it means the future of AI isn't just about making chips faster, is it? It's about smart strategies, system design, and that constant battle for developers. It really shows how massive demand in a field like AI can force even the biggest players to change, and it creates these fascinating new dynamics. Something for you, the listener, to think about: how might these shifts behind the scenes affect the AI tools you use every day? Faster responses, cheaper access, maybe even entirely new capabilities. It's incredible engineering driving all this. What do you think the next big move in this silicon chess game will be?